Okay, Math 3, we're looking at some 3 different relationships within triangles that are all proportional. I'm going to start with what we call the angle bisector theorem up here, and you can just read what it says. I'd remind you what an angle bisector is. An angle bisector is anything that can cut an angle into 2 equal pieces. 2 equal angles, if you want to call it that. So just as a reminder of what that is. So all 3 of these, or both of those, are angle bisectors, I should say. This one and this one are both angle bisectors. If you look at the top, those are equal marks. And what they've done is they've cut these into 2 proportional pieces, and that's what this is trying to tell us. So we're going to highlight those proportional pieces. Okay? In green, CA, and in blue, CD. Notice that those are both the same side of the triangle, right? So the left side of the triangle. And then over here again, you got the same idea. BA is proportional to BD. Now what does that look like over here when you do some work? Well, if I label these parts that they told me, then I can simply set up a proportion exactly like I did over here using these numbers. So 12 is going to go to 6. 12 over 6. And over here, the blue and the purple, so over here 15 over x. And at that point it becomes a solving problem, and you just solve it. So we found out that the angle bisector does divide these big triangle into 2 smaller triangles whose sides are proportional. Okay. We also found out that the angle bisector is not necessarily the median. We did a lot of work with medians last week, and even though this might look like a median, because that was a 7.5, this clearly is not the midpoint. So it is definitely different than the median. Alright, take a minute to go over that a couple times. We're going to look at side splitter next. The side splitter theorem tells you that if you have any line parallel to a side of a triangle and it intersects the other 2, like over here, this line is parallel to this side of the triangle, and again up here, then it's going to divide those sides proportionally. So specifically, we look at the different proportions that are there. Alright, I think you can see that AB is going to be proportional to AC, that chunk over there. And then in green, you've got BD is proportional to CE, that little chunk there. In other words, if you slice this triangle, as long as your slices are parallel, you're going to make proportional chunks every time. Now, there's 2 more things that happen to be proportional. One is BC and CD. They happen to be proportional, not technically by the side splitter. It's actually by a different reason, but it fits in well here. And then by the side splitter, you can tell that the AD and the big sides are going to be proportional. So an example would look like this. Alright, and that was actually 2 examples. Sorry about the speed. You can go back and back up if you need to, just a few minutes, and watch this second one. The reason that the side splitter works on these, even though they're not triangles, is I could very, very, very easily just make these into triangles, couldn't I? Just by extending these points up, dot, 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 and boom, now it's a triangle. So now this situation is the same as these situations. Alright. Once again, take time to look at that. We'll go over our last thing, angle similarity. Alright, angle similarity tells us that 2 triangles are similar and thus proportional if any 2 angles are congruent. Okay? What I like to do on my congruent, my similar triangles, is I like to see each triangle separately. So I noticed there was a small triangle here, so I'm just going to redraw that and label what I know about it. And then I'm going to redraw the big triangle and label what I know about it. Now notice the length of this was 32 only from C to B, but then from B to A there was the other x. So when you add 32 and x together, that gives you this. Now it's so super easy to see how these two line up and they're proportional to each other. So I write a proportion. This x is proportional to that side, 32 plus x. And then 60 is proportional to 80. From there you cross multiply and solve. And you can do that on your own as often as you need to, or slow down. This middle example here, once again, I like to highlight my triangles. Okay, so I hope you can see the big triangle is 85, and even though there's not a question here, I think it's obvious we're trying to find the height of the flagpole, so I put an X right here. Alright, and then the second triangle is where the boy is. So I label what I know about it. And once again, I hope you can see how what matches. X is going to match the 6. So X is proportional to 6, the same way that 85 is to 10, and then it just becomes a solving. The last example is similar by angle-angle similarity. Actually, all of these are similar by angle-angle similarity. I forgot to point that out. But down here on this first one, did you notice that both of these triangles were right triangles? So that's one angle. And they both shared angle A. So this one, even though I forgot to write it, is definitely angle-angle similarity. This middle one, they both have a 90-degree angle, and they both share this bottom angle down here. So again, angle-angle similarity. But on this one, you can see angle. You definitely have those two angles. So I'm going to draw my triangles, highlight them. Hope you can see why that's a 16. 6 plus 10 here gives you the 16. And then I draw my smaller triangle. And notice this side, I don't have this side, but if I knew if I did 15 minus that x, that would give me this side. So that's 15 minus x. You can see which sides match now. You write a proportion and solve. Check out your homework tonight and have some questions ready for me tomorrow. Thanks.